Assalamualaikum and salam sejahtera. Welcome to topic 3 of CST 569 Principles of Compiler. Previously in topic 2, we have taken a bird's eye view of the whole compilation process, and we have established that there are 3 phases of compiler: lexical analysis, syntax analysis, and code generation. Now in topic 3, we will be taking a deeper look at the first phase in compiler, which is lexical analysis. So here are the things that we would like to achieve by the end of this topic. So first, we should be able to define what is a formal language and what is a natural language. Next, we'll be able to list elements of a language. Third, which is a very important skill, the ability to construct a finite state machine and regular expression from language description. Fourth, able to convert a finite state machine to regular expression and vice versa. And finally, fifth, we'll be able to implement the techniques for building compiler tables. However, in this particular video, we will be discussing from 1 until 4 only, and we will discuss how to build tables, especially in compilers, in another video. If we recap back what we know about compiler, it is essentially a translator. So it translates from one language, for example, English, to another. So for example, Malay. Therefore, language is a very important concept in compiler construction. Generally, there are 2 categories of languages in the study of computer science. First is formal language. Formal language can be used with computers. It is a language that can be defined specifically. Each words in this language can be listed and they are known. Examples are programming languages like Java or C++. The next category of language is natural language. Natural language is language used by people. It cannot be defined perfectly because it keeps on changing. New words keep on entering the vocabulary of the language, and the structure of language construction can be very informal. One word can also have more than one meaning. For example, the languages that belongs in natural language are Malay, English, Korean, Japanese, and many more. To study formal language, we need to understand language elements. Some of these concepts may be familiar to you. These are some things that we have learned in mathematics subjects and even in discrete structure, but let's discuss them again. First, set. Set is a collection of unique objects. The number of objects inside a set can be infinite as long as they are unique. So for example, if we have a set that has boy, girl, animal, this is the same set as this second set that has boy, girl, animal, boy. So even though the second set has 4 elements inside of it, it is equivalent with the first set since the element boy is duplicated here. We also need to understand the concept of empty set, which is a set with no element. So it can be represented as this, an empty set that has no element, or this symbol. Next, let's discuss string. To understand string, we need to talk about alphabets first. Alphabets are finite or countable set of symbols. For example, in English, we have A, B, C up to Z. So these are 26 symbols or letters. In Arabic, we have Alif, Ba, Ta, up until Ya. So these are all 29 letters. String is a list of characters from a given alphabet. A string doesn't have to be unique. For example, two strings can have the same alphabets in it. However, order is important in string. So let me give an example. This string AAB and this string BA both have the letters A and B inside of it, but they are not the same strings since order is important in string. Null string, meanwhile, has no character, so it can be represented as this, just like when you are checking if user does not put anything in your program, you will check if input equals to empty, like this. So this is empty string. This null string can also be represented with an epsilon symbol. So this is the epsilon symbol. Finally, number 3. Language is a set of strings from a given alphabet. So for example, if we have the alphabet with two symbols, 0 and 1, the language that can be constructed from this alphabet includes 0, 1, 0, 1, 1, up until all possible combination that can be made from 0 and 1. Another example is, if we have the alphabet characters from the keyboard, from our keyboard, the language that can be constructed from these alphabets are Malay language, Java syntax, English language, C++ syntax, and many more. As humans, we instantly know whether a word belongs in a language or not. For example, if you have these 3 words, kucing, vacation, and pinggan. From these words, we can instantly say that both kucing and pinggan are Malay words, but not vacation. But how do we teach machines to differentiate between words that belong in a Java language, for example, and words that are not? Let's say we have these reserved words of Java. So we have class, we have inherits, and we have cupboard. How do we design a machine that can accept the first and the second word, but not the third? A way of designing this is through finite state machine. It is a machine that can have as its final state the status of accept, or reject based on the input given. So for example, if let's say we manage to design a finite state machine for Malay language, when we put in kucing into it, the final state will be accept. However, if we put in vacation into the machine, the final state will be reject. A finite state machine has a finite set of states, a finite input alphabet, and a state transition function which specifies the machine state given its present state and the current input. Why do we need a finite state machine? This is because we need a better way of explaining all strings that belong in a language. Let's say if we have a language and the strings that made up this language is A, AA, AAA, and so on. We can perhaps describe this as a language that has a single and increasing amount of A and only A in the string. But what if our language has this string? A, AB, ABC, CABB, and so on. It is now harder to describe which strings are in a language and which are not using English sentences. How does the finite state machine work? So first of all, we have input, which are strings of symbols from an input alphabet. Then we have the machine itself that is initially in a starting state. Next, we read our symbols, and the machine will then change state based on the transition function on the input symbols. Finally, when all inputs have been read, the machine will either be in an accepting state, which means the input string has been accepted, or a non-accepting state or a reject state, which means the input string has been rejected. Whatever strings that are accepted by the finite state machines form a language. This way, finite state machine precisely define all words or strings in a language. There are two ways to represent a finite state machine. The first one is state graph and the second one is state table. Here are the components of a state graph. First, the state will be represented by circle. Transition function will be represented by an arrow with an input on top of it, input symbol on top of it. The starting state is represented by the state with an incoming arrow, and the accepting state is represented by a circle with a smaller circle inside of it. Meanwhile, these are the components of state table. First of all the state names will be inside rows, and all the input symbols will be inside columns. Each entry is the next state of the machine given an input. Starting state is always the one or the first one in a row inside our table, and accepting state will be denoted by asterisk. The type of finite state machine we'll be using is deterministic finite machine or automata. This type of machine has one and only one arc, leaving each state for each input. For example, if you have an automata with two states, A and B, and the input alphabets are 0 and 1. State A, which is now the starting state, must have two arcs leaving itself, two arrows, one for arrow 0 and one for arrow 1. Okay, so for example, one for arrow 0 and one for arrow 1. Same goes for state B, which is now an accepting state. State B must have two arcs leaving itself, or two arrows, one for arrow 0 and one for arrow 1. So something like this, the one that I have just shown on the screen, is possible. But if you have a finite state machine that looks like this, so it has two states, A and B. A the starting state, B is the accepting state, and then you have only one arc leaving state A with the input 1 and only one arc leaving state B with the input 0. So for each of these states, like for state A, it is missing input 0, and for state B, it is missing input 1. So this is not possible. This is not a deterministic finite automata. Let's take a look at an example of finite state machine. This machine accepts any strings of zeros and ones that contains an even number of ones. First of all, based on this statement, we should list down what we know. First, input alphabet is 0 and 1. Next, even number. Even numbers we know starts from 0, 2, 4, 6, 8, and so on. And then we should list as much as possible the strings that can be accepted by this machine. The rule of thumb is to start with the shortest accepted string. So let's try to list down as much as possible. The shortest accepted string for this would be epsilon. Okay, since 0 is an even number. So if we want even number of ones, epsilon is part of this language. And then we have a single 0. Then we can have 1, 1. Remember, if we want to put 1, the 1 must be in even number. Then we can have 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, and so on. Now let's see the state graph. Okay, and now let's verify this state graph. So this state graph has been given to us to see whether this state graph correctly represents this explanation. We're going to take a look at the strings that we have generated. Okay, so first of all, epsilon. Epsilon is true. Why do we say epsilon is true? This is because the starting state A is also an accepting state, which means it accepts a null string. Okay, therefore, epsilon is correct. Next, 0. Okay, we start with A, then we go 0, and this is an accepting state, therefore, 0 is accepted. Next one is 1, 1. Okay, 1, 1, and accepted. Okay, this is correct. And then 1, 0, 1. 1, 0, 1. Accept. So this is correct. Next, 0, 1, 1. 0, 1, 1. Accepted. So correct. And then I'm going to check the final one. 1, 0, 1, 0. 1, 0, 1, 0. Accepted. Correct. So we can say that this state graph over here given to us correctly represent a machine that accepts any strings of zeros and one that contains an even number of ones. Next, what we should do is to represent this in the form of state table. To do this, what we do is, first of all, we create the table. The states would be on the rows part. So we have two states, A and B. A is in the first row since A is the starting state, and because A is an accepting state, I'm going to put an asterisk next to it. And then we have two input strings or two alphabets. Our input strings would be on the column part. So our input strings are 0 and also 1. Okay, next we need to translate from on the state transition function. Okay, let's take a look at state A first. Okay, A to 0 goes back into A. So I'm going to put A here. A to 1 goes to B. Okay, next let's take a look at B. B to 0 goes back into itself, B. And B to 1 goes to A. So this is our state table. So if you see clearly, there is no empty cell inside the state table, which means this is a deterministic finite automata. Okay, next question. String that contains odd numbers of zeros and input alphabet is 0, 1. So let's extract what we know from this question. Input alphabet is still 0, 1. But then we want odd numbers. So odd numbers we know start from 1, 3, 5, 7, and so on. So if we want to list a string of accepted string, so we start with the shortest accepted string. The shortest accepted string in this particular example would be 0. Okay, because string should contain odd numbers of zeros. Next, we can have 1 0, 0 1, 0 1 1, 0 0 0, 1 0 1, 1 1 0, and so on. So if you notice, all of the strings that I listed here, they all contain odd numbers of zeros. Okay, now let's take a look at the state graph for this statement. So this is the state graph given to us. Now let's verify whether this state graph is true. I'm going to start with the first string. So 0. So starts from A and then 0, and it falls in an accepting state, which means the string is accepted. Okay, the second one, 1 0. Okay, 1 0, 1 starting from the starting state, 0, and it finished at an accepting state. So this is also correct. Okay, now the third string, 0 1, 0 1, accepting state, correct. The third one, 0 1 1, 0 1 1, accepting state, correct. So I'm going to test the final one. 1 1 0, 1 1 0, accepting state, correct. So we can safely say that the state graph given to us here correctly represent this statement. Next, let's draw the state table for our state graph. So we have, draw the skeleton first. So we have two states. So A is the starting state, so it is in the first row, B on the second row, and B is an accepting state. I'm going to put an asterisk next to it. So our input alphabet is still 0 and 1. Okay, now let's fill up all the cells with the information. Okay, A with 0 goes to B, A with 1 goes to A, B with 0 goes to A, B with 1 goes to B. So all the cells are filled. Therefore, we confirm that this is a deterministic finite automata. So here is another example. Strings that contains 3 consecutive ones and the input alphabets is 0 and 1. So I'm going to list down list of possible accepted strings, and rule of thumb is to start with the shortest accepted string. So the shortest accepted string is 111. Then next it can be 0111, 1110, 1111, 10111, and so on. Okay, now let's take a look at the state graph for this statement. So this is the state graph. You can verify whether the state graph correctly represent our example 3. So I'm going to test the first string. Okay, 1 1 1. So D is an accepting state, so this is accepted. I'm going to test the final string. You can also check the rest of the strings if you want, but for this example I'm just going to test the final one. 1 0 1 1 1. D is an accepting state, therefore this string is accepted. Okay, and the state graph for this, the state table for this state graph is this one. So you can check later whether this state table is correct. So we are done discussing finite state machine. There is another method for describing language, and that is regular expressions. The 3 possible operations in regular expressions are union, concatenation, and clean star. So the first operation that we will discuss is union. The results of union of operation are 2 sets. So for example, if you have this set ABC AB, BA, so this is the first set, and we want to union it with the second set that has the elements BA and BB. The result of a union operation is just all of the elements inside of the two sets. So we have ABC, we have AB, we have BA. And from the second set, since BA is the same thing, and remember set is a collection of unique objects, you do not need to list it again. So this is already included, and then BB. So this is how you do a union operation on two sets. Next, L union with an empty set would get the language itself. Concatenation, meanwhile, combines two strings to form a set of new strings. This is like doing an expand operation in mathematics. So for example, if we have this set, the first set, we have this inside of it, these elements. We have A, B, A, and C. And then we want to concatenate it with the second set that has B and epsilon. So to do a concatenation operation is like an expand operation. So A, B, and B, we will get A, B, B. Okay. A, B, and epsilon, we will get A, B. Next, A with B, we get AB, but since AB is already inside our set, so we skip it. Okay, A with epsilon, we get A. And then C with B, we get CB. And C with epsilon, we get C. So this is a result of a concatenation operation. Okay, so that was the first example. Next, if we concatenate a language with a set with an epsilon inside of it, we get the language itself. However, if we concatenate a language with an empty set, we get an empty set. The third operation of regular expression is clean star. It is a unary operation and it is also sometimes called as closure. It is designated with an asterisk. The operation of clean star is like this. So if L is a language, we always start with L to the power of 0, where L to the power of 0 is a set with an epsilon inside of it. L to the power of 1 is the language itself. L to the power of 2 is language itself concatenated with L to the power of 1, the result of the previous operation. Okay. L to the power of n is the language itself concatenated with the result of the previous operation, language to the power of n minus 1. And finally, L star is the result of the union operation of L to the power of 0, power of 1, 2, 3, 4, up until infinity. So this is an infinite type operation. Here I will demonstrate the clean star operation using example 4. Given a language with two elements, 0 and 1, find L star. So we will start, remember, we will start with L to the power of 0, which is always epsilon. L to the power of 1 is the language itself, which is 0 and 1. L to the power of 2 is the language concatenated with L to the power of 1, which is 0, 1, concat with this. Okay, 0, 1. So what do we get? We will get 0, 0, 0, 1, 1, 0, 1, 1. Okay, so that is L to the power of 2. Now, L to the power of 3 is the language itself concatenated with L to the power of 2. So it will be 0, 1 concatenated with this. So it will be 0, 0, 0, 1, 1, 0, 1, 1, which we will get 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So that is L to the power of 3. You can continue L to the power of 4, 5, 6, and so on. But I'm going to jump directly to L star, which is the result of the union of operation of all of these L's. So L to the power of 0, union with L power of 1, union with L power of 2, 3, and so on, which means we're going to need to list down all of these elements that we have extracted on the previous step. So it's going to be first epsilon, and then 0, 1, and then 0, 0, 0, 1, 1, 0, 1, 1, and then this one 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And remember, we are not done because this L operation can be done to L to the power of 13, L to the power of 100, L to the power of 430, until it is like I said, it is unending. Okay. What is shorthand notation? Shorthand notation is simply a way of removing the curly braces. For example, here we have 0 plus 1 or 0 union with 1. It is actually a union of two sets. The first set has a single element, which is 0. The second set also has a single 1 as its element. Therefore, 0 union 1 is actually a set with two elements, 0 and 1. Okay. As for the second one, 0 union with epsilon, you get a set with two elements, 0 and epsilon. When doing regular expression operations, this list of precedents must be followed. The first one is everything inside the bracket must be operated on first. Next is clean star. So the next precedent is clean star. Third is concatenation, and the fourth one is union. Now let's take a look at a final example on regular expression. So we need to do this operation, but this is using a shorthand operation. But do not get confused because this is actually, if you remember on the previous slide, this is actually two sets union together and you get this. Okay, and then we need to do a clean star operation on it. So 0, 1 clean star. But if you still remember, we have done this operation before, the clean star operation, exactly as this, and I am copying the result of the previous operation here. So we have this is basically an unending, but we can safely conclude this as all possible combinations of 0 and 1, including epsilon until infinity. So all possible combination of 0 and 1. Any strings that have 0 and 1 would fall under 0, 1 star. Okay, now what we need to do next is to concat this string that we have generated from the previous operation before, which is the result of 0, 1 star, and concatenate it with 1 at the front and 0 at the back. So our language here will be 1 concat with epsilon, we should get 1 back again, concat with 0 at the back, so it will be 1 0. Okay, next is 1 concat with this 0, concat with another 0 at the back, the green 0 at the back. Okay, next for this one, 1 concat with 1, concat with the green 0 at the back, and the next one is 1 concat with this 0 0, concat with the green 0 at the back. So there are so many elements here, so I'm just going to skip to the final 2, this one. So dot 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 dot, and then we have 1 concat with 1 1 1, concat with the green 0 at the back, and the final one, 1 concat with this 0 0 0 0, and concat with the green 0 at the back, and so on. So this is how you do a regular expression. And if you look at this example, it is a combination of a clean star operation, a bracket operation, a union operation, and also a concatenation operation. And so I hope you understand how to operate regular expression type question. Thank you.